So, okay. And should I start, or what do you think? It's 5 after.
Hey, you're good.
So, my name's Steve Yucks. I work for Montrose Environmental. I'm the Vice President Technical. And I am in the Emerging Technologies Group, which is a small group of us who look at new technologies that are available, do the R&D and development work, and then bring them out into the field as a general use. I moved over and started working with the group in January of last year. So, so I'll talk about this. I'm going to talk a little bit about HRVOCs because that's a big issue in Texas. A little bit of the OHAP analysis, and of course ethylene oxide. And you have to throw in a little BTEX because everybody loves BTEX. So, so I had a lot of other instrumentation stuff in here, which is kind of in this, but it ran way too long. So I'll talk a little bit mainly about fence lines, since that is now an emphasis that our group has been tasked with. And we have a person in Denver who is doing the low-cost sensor work and making intelligent sensor networks that communicate in real time. So he's doing that part of it, and then I'm doing some of the open path and other technologies that are around for that. And then I'll spend a lot of time on the proton transfer mass spec that we have in its uses. And then a little bit, we recently acquired a sensible IoT programming company, and we're working together to develop some different software solutions for the analyzers that we have there and some of the other sensor work that we're doing. So I'll talk a little bit about that. And the main emphasis for what we're going to do is on leak location, community monitoring, which is a new area for us, incident response, and then some real-time mapping. And I'll give you a few examples of those. And my coworker, Dr. Zemrick, is just in, so he's on this paper too, so he's in the back. So if I have questions, you have questions that I can't answer, he can. So I kind of skipped over the sensor networks because most people know how those work. They're stationary, they're deployed out in the field at a fixed location. They run for a certain amount of time, and then they're taken in, or if they're a real-time sensor, they alarm. Which is great if you have a fixed location that you're worried about, but if you're trying to monitor an entire fence line or a facility boundary, you need to look at some other kind of techniques. And one of the newer ones that are out there is the open path, and especially FTIR, or even the UV-DOAS systems that you deploy. You can see through the point here in the center where this is kind of my little pollutant cloud that will drift up this way and be picked up, or it's coming this way. The UV-DOAS, of course, they're not next to each other, but they come across the beam path and are analyzed. And this is really what you're seeing here. So if you look at these, you have point samples that are located along the fence. And then you have this beam. If you don't have the point sensors and you just have the beam, you don't really know what's going on here. You don't know the extent to which this plume, the concentrations of it, or where it's at. It's really just an alarm system. So, in this case, then this top spectra where everything is all 10s across will give you the same results as this one that's 0s all the way around, but then a really high concentration in the middle. So it's really a very nice alarm system. And there's some other issues on how you validate it and audit these kind of results. They work well, and they have a great use. And this is actually setting one up out in the field. So this is the IR source, and you can see here, the lines aren't there, we drew those, but those are the reflectors in the back. So this is set up inside of this little doghouse with the holes in it, and this is a rotating turret that moves around, so it moves the IR beam from different places to different ones, and then you take your measurements, and you can set this up anywhere that you have a straight line system that you want to see something. So this was done at an ethanol loading facility, just as a client had some questions. So I'm sorry the pictures are a little blurry. They didn't cut down very well, but you can see there's some locations here where the beams were set, and all these green dots represent positive hits. So You can see from here over, you're picking up some, you're picking up here. If you take that and then, oops. So if you take these back and look at this, okay, sorry about that. This traced back to, it's hard to tell, these are the semi-tanker trucks, and they have the big hoses that they hook on and fill, and then when they unhook them, there's still product in them. Well, that was the product that was causing all these positive hits for the ethanol system, so they put in a recovery system to handle that. I'll move on. So another big interest for us, and this is for all the sensors that we have and the mobile platforms that I'll talk a little bit later, is you can have all the sensors that you want, but you need to know where the material's coming from. So we've been, like I said, we've been working with Sensible IoT, and they're developing something that will go back and triangulate some leaks for us. But in this scenario here, you have a point sensor here, whether it's a reflector, mirror, or a fixed sensor, or a portable EGC system that's set up in these locations. Depending on which direction the wind's blowing, it may hit over this sensor and then hit over this sensor. So you can take the wind data, the vectors, and the concentration numbers, and use the orthogonal vector analysis to come back to this point. And that's what this is, and this is a real world wound. And I'm sorry, once again, it's hard to see, but I want to make sure that I get exactly right what I'm saying. This is covering up my note thing here. Yeah, so this alarm, these were set on an actual one sensor, which is over here on this side. One is here and one is here on those two. One was on a roof, one was on ground level. And this was actually in Denver, I believe. And they used this to concentrate and used after, I think about 2 weeks of analysis that there was a vent that was leaking at this location. They went back, closed it up and took care of it so that they didn't have that issue anymore. This is another one, same type of analysis. You've got a whole row of sensors here. By looking at the data, the concentrations and the winds, you can go back and look and see where the analysis is. And this is great. Oops. Well, that's the next one anyway. So, and that's great if you if everything hits right where your sensors are located. But if you have gaps in the middle, you can have some misses in coverage. But most of the sensors, as you know, are relatively high, not high in concentration, but they don't have the greatest detection limit. So they may miss something that's below their threshold. So there's a need for a lower detection system, and one of the really effective cost-effective alternatives is the optical enhanced FTIR, and it's a regular FTIR system that is adapted, and this one is actually made by Max Analytical over here on the side. But so in a normal FTIR system, this is your baseline. The green, you've got the range of compounds anywhere from 4,000 down to 400 reciprocal centimeters, depending on which window materials you're using. And you're looking across that whole spectrum there. What optically enhanced FTIR is a set of filters and some electronics modifications to the laser system. And now, instead of having this whole bandwidth that may interfere here and here, now you're just looking at this really narrow window. And what that allows you to do is you can tailor that window to whatever particular frequencies you're most interested in for your analyte. That allows you to lower the detection limit considerably. And these go by several different trade names. Probably the most common one is the Star Boost system. We have multiple ones of these. We have them for ethylene oxide, formaldehyde, and we're actually working on now one for acrolein, because that's becoming a rather hot topic area too. So this is kind of a nice way to take this is another stationary system. You can't put it in a mobile platform, and I'll talk about that in a few minutes, but this is a nice way to take a very versatile instrument in the FTIR, be able to change out a few key components and make it a much more robust, lower detection specific analyzer. So pretty good bang for the buck compared to the cost of some of the other systems. So we have these. They are mobile. These are used for temporary SEMs very often. They're working on some of our other competitors and other manufacturers in the instrument industry are working on various different models of this. Some use cavity ring down, which is a relatively new technology, which does give very nice detection limits. And so, everyone has their own little niche. These are used mainly for the temporary SEMs. We put them in the van, but they're all fixed. And we want to be able to move. We want to be able to go around. We want to be able to look and see where these leaks are. So we chose to use mobile time of flight mass spectrometry system. And I'll get into that in a little bit. But so many of you may have seen this is sitting out front. And if anyone wants to come and see it afterwards, I'd be more than happy to show it to them. The insides. So this van has a Inficon 6000 X3 PTR time of flight mass spec. I'm getting a little tongue-tied, sorry. This is one of two that are in the world. The other one is at Ionicon. This has the upgrade that makes this one more sensitive. So for a lot of compounds, we're seeing low part per trillion detection limits in real time. So in 1 or 2 second analysis. So this is the person who actually built the van out and works with me. His name is Art, and this is me in the back of the van. So what is it? It's a great big name, but basically what it is. So we use this to ionize VOC or even some inorganics. So you take a reagent gas, which in these 3 cases here is water, oxygen, and NOx, NO. You make an ion, which is what happens here. So it comes up in this little chamber, it gets ionized, it then flows across a diffusion portal here. Your air sample comes in that you're drawing in with the VOC. They come here, they mix together in the chamber, and they kind of drift down the chamber. Well, they're shot down the chamber at high speed, and then they go to the mass detector. And since it's a time of flight, the faster they are, you have less momentum. So you measure the time that it takes for that ion to come out of the source and hit the detector plate. So we do that here, and I'll go into a little bit more detail on that. But and we have this van interface with a bunch of other equipment besides just the PTR. We have a weather station with a high resolution GPS in it. We have some networking programs in there that allow us to take the data, send it up to the cloud, do real-time calculations, and bring it back down to the platform so that you can see it in real time. We can equip this with an FTIR. We can equip it with Starboost system. We've done both of those many times. I also have a GC that I can interface with the PTR if we need to do that application. Most of the time we try to avoid that simply because when you have a GC involved, you have a finite time that you do an injection and it takes for those components to come down the column. That may be 2 minutes, it may be 25 minutes, just depending on what you're trying to separate in the length of the column. So when you do that, you're really no longer in real time. You're getting a shot every 20 minutes or however long it takes to do the separation. So we try to avoid that whenever possible. Sometimes we do have to do it, and I have a couple examples in here that show that. So when I say proton transfer, what are we really talking about? So we use water, NOx, or oxygen as the reagent gas. We introduce them to the ion source. It creates an ion. That ion then interacts one of several ways with your molecule of interest. You get the proton transferred over, which is the most common mode. You can associate and make a little cluster of a lighter molecule with the NOx, and then you increase the mass, so it becomes a little easier to detect. Or you can do oxygen, which transfers the charge over but doesn't add a proton. So there's several different ways we can do this, and we choose which one of these we're going to use based on proton affinity. Well, that was a big change. So this is kind of the Proton Transfer Bible here. This is our little guidance book that we use for everything. So earlier today, several people had asked me what components we can see with the Proton Transfer instrument. So you go and look. Oh, and by the way, we can do TCE. So we can talk about that later. But yes, I found out we can do it. So sorry about that. So we look for, let's say we're interested in doing analysis for isobutane. Since the proton affinity has to be higher than the analyte reagent here is water, so we can't use water. It won't work. But we can use NOx or oxygen to see it. This allows us to tailor what set of molecules that we actually see. If we choose this, we see everything above it, but we don't see this down here. So this can clean up the spectrum and make it a lot easier for interpretation, which is critical because this is I'll show you later, this is a very high resolution instrument. So there are a multitude of peaks that we get on a lot of this thing. So, but 95% of the time we run in the water mode. It gives us the highest detection limit usually, and it works for most of the ones that we need to see. So now I want to take this and talk to one of the biggest problems that we have that I was tasked with when we first started, and that's the ethylene oxide quantification out in the environment. Unfortunately, in a lot of the earlier work for ethylene oxide, there was a lot of reports of really high concentrations of EO, and it was actually EO and acetaldehyde together. If you don't use the GC column and you use the normal ionization mode, you can't tell the difference between them because they both have the same molecular weights. So that's a problem. That's a huge problem. Now, laboratories that pull swim canisters and do those analysis, those are usually done down a very long column, 105-meter column. So they do get the separation found, but you still have some drag in there. But you can't do this in real time. So we need to come up with a way to see that we can separate out ethylene oxide from acetaldehyde. And we really kind of did that by going back to that guide that we were talking about before. But first, I want to give you an example. This is an actual GC trace of it. So we do have column systems that will separate these two out, very easily. And then you can run them. You can take the effluent out of the column system and run it right into the mass spec, and you see the two peaks at the parent weight of 45 because you're adding a proton to it by the proton transfer. So instead of 44, it's 45. So if you monitor that mass, you see these two peaks. So it comes through, the acetaldehyde comes in first, goes back down, and the ethylene oxide comes back, and you go back down to baseline. It takes about 4.5 minutes to do one of these injections. But we really wanted to do it in real time, continuous. So we looked at trying to do some association reactions and work on the difference between an epoxide ring and an aldehyde group. So we're gonna look at this, see if we can do something with this chemistry to make it happen. So if you change reagents from the hydronium mode back to oxygen, when you put the oxygen reagent into it, you generate these two species, which is dioxygenyl and then hydridodioxygen. So it's a mouthful, but it's oxygen with the hydrogen stuck on it, okay? You allow them to react and you form this complex over here on the side, which is an association complex through the lone pairs of the oxygen. So now you've changed the molecular weight of this species from 44 to 75 and 76. Now, if you're looking at the slide, you're going 32 and 44 is 76, and 33 and 44 is 77. But what happens is when this forms an association product, it kicks out its hydrogen. It's not stable. It throws the hydrogen back out, and this it loses hydrogen. So then you have a 75 and a 76. So it does an association, it does a rearrangement, and you end up with these two peaks. And that's great. And you say, well, that's great, but acetaldehyde has an oxygen, so maybe it does the same thing. So we needed to prove that it doesn't. And this is how we went about it. So if you take a straight trace going, you can introduce calibration gases directly into the PTR, and you can use, so We did a nice nitrogen baseline, monitored here. We shot 2 ppm, which is sky high for this, but you put that through and you see no increase in signal, and then you switch over to ethylene oxide and you see the big jump in signal. And that's what you're seeing over here. So we're monitoring masses 75 and 76 now, and you see these going up when they're formed. And these are corrected counts, and I'll show you a little more detail about those later, but you can take those values and determine a calibration curve. And you can quantify your ethylene oxide directly by injection. This is a little bit more detail. So if you're looking at that, this is the mass of 44. So this is proving that the acetaldehyde won't cause a false positive in the ethylene oxide. So we did the ethylene oxide first to show that it didn't show anything from acetaldehyde. Now we're going the other way. So you inject acetaldehyde and you monitor these different masses. So you can see there's no response down here for the 75 and 76 species. So now you've got a system that will work in real time that allows for direct quantification of EO without any interference from acetaldehyde. And it's a big deal because acetaldehyde is pretty ambiguous. I mean, it's everywhere in the environment. You know, if you're near a combustion source, it's there. If you're in a paper mill, it's there. A lot of industrial plants, so it's there. A lot of fuel places, ethanol plants. It's a huge. It's there everywhere because it's one of the side products from the fermentation process. So it's easy to get the false positives. That's for sure. So now that we have this, we have a system that works. I always want to go, let's take it down the road and see if it'll work. So we decided to take off and see if we could do a little real-time mapping with the instrument here.
Oh, here we go.
So this is a real-time plot of ethylene oxide as we are driving. This is the north side of Chicago up here. There's a stadium around here. And you come a little bit further down and there is O'Hare. And so we wanted to monitor around there because there has been some complaints about the exhaust from all the jets and everything. So you can see real-time contributions, and these are they're a little bit less than a ppb in real time. These numbers are about 150 to 200 ppt. I think that was 800 something. ppt is the highest number. But it's there and it's real and it's measurable. So a lot of our clients that use ethylene oxide for certain procedures like to have their facilities mapped to see if there's any hot spots or any leaks that they have, and we use this tool to do that. So, I mean, this looks great. You're going, well, that looks good. But, what are we really looking at in terms of what is it? I have no idea what that was. So that was pretty cool. I'm going to back up and see that again. Oh, it's a bird. Oh, okay. That was weird. Sorry about that. So if you come out in the van and look and see the display, you guys were looking at this earlier. This is what you actually see this is what I look at as we're monitoring, and it's really just a lot of lines. To be honest with you, but it's the natural log of the mass of the charge ratios of the components that are in the detector. When I first started doing this meant nothing to me too. And the couple of guys who trained me said, oh, you'll learn to use this all the time and live by it. And I said, you're crazy, because the next line is what it really looks like. And that's a lot easier to look at and understand what's going on than the first one. But I will admit, I do use the first one some too, because it tells you if you're saturated and other things. So, but what we're really looking at here, and this is the mass ratio. This is the atomic weights here. So in this particular species, this was a BTEX. So a benzene, toluene, I can't see the pointer, toluene, and then the ethylbenzene and xylenes, those are all one peak, because we have an issue with isomers. You can't separate isomers out on this, and we'll talk about that in a little bit later. So when I first generated this, I was really confused because I could not for the life of me figure out this peak was and this peak. And I learned the hard way that you don't shoot thiophene and styrene through an embryonic system because you never get them back out. So this is from an analysis I'd done maybe a week prior. I ended up having to flow about 2 days through all the different mass flow controllers continuous to get it all flushed out. So word of advice, don't shoot that kind of stuff through there. It was terrible. So what do? We take those gases now, and I'm from a stack background where you have to calibrate everything directly. You have to be able to show your traceability. So that's what I try to apply with this, and that's what this is here. These are different calibration values that I've shot through, at different concentrations. This is, I think this is just, this is benzene, toluene, and the xylenes. So shoot them at different concentrations. You get the stair steps, which are really familiar if you've done any kind of analyzer work. That's the kind of, if you plot out an analyzer response area, that's what you see. And this bottom is what's called the direct mode, which is what I usually run in. And this top one is called the funnel on mode, which is used for really, really low concentration measurements. This is what distinguishes this instrument from most of the other ones out there. We can turn it's called an ion funnel, and it guides everything down into a really tight pinpoint. So think of having a flashlight and turning it on with the normal beam, you can see a pretty good spot a distance away. If you take that flashlight and it's adjustable, and you turn the lens, you focus it in, you don't see all the way around, but you see a lot smaller spot and a lot higher definition. And that's really what this does to the ion. So it allows us to really, really lower the detection limits. So, you think, well, that's great. We generate all these things. So what are you going to do with them? I'm going to take all this and I'm going to generate direct 5-point calibration curves for almost every species that we measure. And this one happens to be benzene, toluene, xylenes. Again, these are different modes of operation that I use depending on different circumstances, but I have hundreds of these that I've generated for all kinds of different compounds. And I use this slope and intercept to calculate my results in real time, so they're traceable. You can use this to, there's a K factor measurement, which is it's a very valid way to do it as well. It just has a little bit more wiggle room in it. It's usually plus or minus 20%. These are plus or minus 5%. So the K factor allows you to determine the concentrations without having the cylinders there. And I had the equations in to do that, but they didn't bored me. They're just huge bunch of numbers. So, but they do work. They've been validated many, many times, and the EPA recognizes them as well. So once again, we tried the direct calibration. Now I wanted to take it out and see what was, try to do some BTEX in real time here. So luckily, right before we had the lockdown in Illinois, we had taken a road trip from our office up in the northwestern suburbs down to around O'Hare and did some mapping in that area. So you can see this is the benzene number, which is the big one. It's 2.5. This is on I-294, which is the big highway going into O'Hare and from the western suburbs. So you can see elevated, a lot of traffic, a lot of benzene. Not as much toluene and a little bit smaller amount of xylenes, but they're there and they're there in considerable concentrations. When we had the lockdown, Art and I decided we'd go out for a ride anyway with it just to see what the difference was. And this is the same route. We did the same exact route, same setting, same calibration and everything. And you can see the difference now in the benzene number. It's 3.5 times lower than it was before. This is, they were doing road construction and we kind of had to go through there rather slowly, but that's the big xylene peaks from the diesel there. But you can see it was sensitive enough to measure the difference between those. And that was pretty, we were very happy with that. It was very amazing. So of course I like the visual. Again, we like to do the mapping. So you'll see it come in from the upper part up here. So you'll see it around, every once in a while, you'll see these really big spikes here, and you'll see a couple down here in just a second. I'll show you when the map finishes there. So this is that's pretty good concentration there. So we take these data after we make these maps, and we do these for our clients too as well. And then we'll zoom into these areas and see exactly what's around here that might be causing this. So that's one of the services that a lot of people really like. And oh, it started up again. So of course, well, we did a nice little one from the office to O'Hare. So let's see what it looks like. We go from Austin to Houston, and this was actually done at the last live 4C conference. So Pete drove it back from Austin over here, and this is going all the way down. You'll see it go into Houston. Here, our office is on the southeast side of Houston, and you can see these. Down here it gets a little bit bigger. Well, that's a lot of data to pull at and look, all at once. So we'll take these and we'll cut them into smaller pieces, and then we'll rotate them around and we'll work them around. And this lets us zoom in on some of these higher areas that you see. So this is actually 610 that runs through Houston here. So you can see we're in the area where we saw those, the tan here is xylenes. You can see where we started running into some higher xylenes here. So we did a little bit more work. We looked at some of the wind directions and measurements that we had, and we think, and we can't prove this, nor will we even try, but these are brownfields that had been former industrial sites that were taken down and kind of cleaned up and reclaimed, but there's still some stuff coming off of those. So very interesting. This is it's a high speed. This was done at 60 miles an hour as he was driving through. So about every 50 or 58 feet or something like that, you're getting a data point, because this is 1 second. So, and you can zoom it in, and I mean, you can go to ridiculous amounts, and you can kind of lay it back and get an idea of what you're seeing along the route. And then of course I had to get even more ridiculous when we went back from Denver. We were doing a job out there, and we brought that. Have you started? So there it goes. So this, we wanted to look and see all the way across the country, and mainly I just wanted to see if I could push the system to do this, and it worked actually a lot better than I thought it was going to. But so you see, I had to do it in 2 parts, and you'll see here in just a second. So it makes it over to Des Moines, and we're going to come in and flip back, and then we're going to follow it the rest of the way. So we're across Nebraska, Iowa, and now we're coming into Western Illinois, and then you're going to head up to Chicago. And I was actually surprised to see this one and this one. And if you go back, if you zoom into that, this is the huge, they claim they're the world's largest truck stop on I-80 in Iowa, in the Illinois-Iowa area. And that's right at this area. And this is a huge truck stop that's in Nebraska that they went through. So you can see that the immediate environment around these facilities are changed by what's going on, and it was amazing to us that we could see that. So I'm going to switch a little bit from some of the mapping stuff and talk a little bit about some HRVOC compounds. I better pick it up here. If you're from Texas, you know that they're pretty highly regulated in Harris County, and they are ethylene, propylene, 1,3-butadiene, and the butene, the 4 butene isomers. So there's a bunch of rules, and they're very highly monitored and very highly regulated species. So we wanted to see if we can see this with the time of flight instrument in real time. So we're looking at it, and I don't expect you to remember because I don't, but if you go back and look at the chart that we were looking at, if you use the water mode, you see everything except ethylene, and you can't see ethylene, and that's one of the predominant ones. So I switch reagents back to oxygen, and this is, oops, sorry about that. And this is actually the ions from all those same steps. And I calibrated down to 3 ppb. The detection limit that we determined was about 82 ppt for ethylene, which has got the highest detection limit. So the other ones we can see lower. In Harris County, I know that the limit is 50 ppb for total HRVOC. So, we can use this to see quite a bit, and they are summed. So if you're at your detection limit by another instrument, it's counted against you. So that can be a big issue if you have a very large facility and you've got a lot of HRVOC sources you have to report. So this offers a way to get that number lower and lower your total emissions of HRVOCs. There are some instances where we do need to be concerned about the 4 butene isomers, and we can separate these out easily with the GC in front again. These are the 4 butenes, that's 1,3-butadiene, propylene, ethylene. Run those through the detector then, and you can come up with that. So there's your detection limits there for summation by total. So it's a relatively very sensitive tool to try and pinpoint if you have some HRVOC problems, especially if they're causing you some issues. We'll switch on and we'll skip all this. So that's really what it looks like. There's the 4 individual ones separated out in the different masses. And so if you want to do these for compliance work, you have to do them by method 18. And we've done all the work for that. We are in the process of writing another test method with the EPA to accept this data. But we're trying to do some proof of concept work. So we shot them all, calibrated to determine the curve, did some testing. Method 18 has some very rigorous requirements. We passed them in the lab, so then we wanted to try it out in the field. So we had a client that we're very familiar with who happened to have 1,3-butadiene in the source that we were doing the stack test on. So we did a side-by-side stack test with the PTR and regular interface GC. So this was all required for the EPA. So we can do the calibrations out in the field. We can do the pre and the post, and there's a sample line loss that recovery you have to do. We passed those criteria. There's the calibration curve that it came up with for 1,3-butadiene. And then, I'm sorry, it's kind of hard to see, but there are 3 different ion traces in here. There's 1,3-butadiene, styrene, and acrylonitrile as the 3 components that we were testing for. You can see them there. So there's one set of calibrations. There's the next lower concentration. There's the next step down. There's the next step down. So you can see there's a direct correlation there. We'll skip that as the detection limits through 130 feet of sample is about 2 to 3 ppb. So we did the Tier 1 validation, which is required to prove that it's a valid sampling method. To make a long story short, that passed fine. So it was a regular stack test. There's the stack. We ran it up through there. There's a little GC interface. And that's for the guys that give me a hard time and say, you don't go out in the field anymore. It's like, there's a picture of me out in the field. So I do. And this is the most important number, which is the recovery. In order for this to be valid, it has to be between 70 to 130%. And 1,3-butadiene was 103 and acrylonitrile was 108%. So they're both valid. I want to look at one thing real quick, which is the new, I've had a lot of questions about how we do the leak determination. So currently we have 2 different methods, independent methods that we use, and one's based on traditional orthogonal vector analysis. So you find a plume, you sit and you monitor, and then you send that data and you take that data and do your calculation. So this is a real world event that we did. You can see here you've got a high point flux at this vector, and then you come back to this one. So at first we thought this was an error, that we have two sources here. No, it's only supposed to be one, but so if you take these results, plot them out on, do the vector weighting here on this slide. You take these results and overlay them with a satellite, and I had to block out a lot of stuff here so it's not, can't determine. Here it is. This is where the test vehicle was sitting. This is that first vector, which is pointing to here, and that second vector is pointing to this one. This tank had a major leak. This tank had a very, very small leak, but they were both leaking, so we did find it. And that vector was correct with 2 of them there. So we actually, this is just one example. We did this from multiple locations around the farm there so that we could get different vector package analysis to make sure that when we went back to the client, and said, this tank is leaking, that we were damn sure this tank was leaking because it's very expensive to fix these. And I didn't want to make the phone call that said, yeah, we told you the wrong tank, sorry. So, so then with our new software partner, which Matt decided to call Origins Analysis, by the way, for some reason. This is that same data package, but this is all the individual points. And I just wanted to give you an idea of what it actually, the data looks like when you start off. It's just a cluster of stuff. And then you run through iterations and you change the weighting factors. And it's kind of a self-learning iterative process that it goes through, but you end up with a result that looks like this. Same place again. We had the van sitting here for one location, here for another location, here for one, and there's a couple that are up here in this other part. All of them vectored back, and these are the weighted vectors. It's kind of hard to see, but if you look right here, it's really dense and it's really heavy. And this is the highest calculated point here. And you can't really see it, but right there is a drain on the bottom of the tank, a roof drain. And when we put we ran an umbilical, we put it in there and it just pegged the instrument. I had to wait about 20 minutes for it to clear out. It was so high, but.
Is that also in-house software?
Yes, yes, this is from the company that we just purchased and we're working with. So this is Matt Beach's software. I don't know if you know him from Sensors, but he's done a lot of work with us in Denver. And then remember that little second leak, this one, this calculation is also picks it up and shows that they're both leaking there too. They have a little higher spread than normal. Usually the circles are a little tighter because your source, isn't this big around. I mean, you guys know how big the tanks are around, so it could be leaking from any, sort. If it's coming off the roof, it's coming from those places. But I'll show you one little closer one that this is what it looks like in real time, and I'm going to have to figure out how to skip this forward. But this is